Hello, everyone. Nice to see all of you. There's a lot more of you than I was expecting. Just as a brief thing before I begin, I want to say it's an honor to be here. Thank you for inviting me to the CFP committee and also to everybody who's interested in watching this talk. Just as a quick little thing, how many of you are from CISPA? Just raise your hand. Okay. How many of you are from Public Club? No one? Okay, one of you. And how many of you are in the Fuzzing Discord? Okay, a fair few. So, reach broadening, excellent. Thank you for coming to the talk. As I said, it's about demystifying fuzzing behavior, or discovering that fuzzing is really just a magic box. Most talks begin with a question of who am I, but I think that's kind of the wrong question. The real question is, why am I giving this talk? Why am I even here, right? The first part is that I care very deeply about education. Before I started my PhD, I was actually a teacher, and one of the biggest regrets of my life is stopping being a teacher, because it was just incredibly important. My second reason for being here is that in science, I think we're becoming too objective-oriented. And by that I mean we're focusing on key performance indicators rather than a true understanding of what we're actually doing, what we are really producing with our work. And third of all, I'm very passionate about scientific rigor. I want to make sure that what we produce as a scientific community is real, is meaningful, is helping us understand things better than we have before. And so we are currently here in this objective-oriented space. I hope by giving this talk, I'm not only helping practitioners to understand what their fuzzers are actually doing, but also push scientists to make it possible for them to understand what their fuzzers are actually doing. So, a bit of prior art. I write a lot about this because I am very prone to ranting. I have written 2 blog posts about this before, and while it's been relatively successful in my own community, at least with some amount of limited range, this talk itself is just broadening that reach, making it more possible for us to talk about this and understand it as a community. And that's important, because right now, research in fuzzing and CS in general really need reform. So, why am I giving this talk? There are critical weaknesses in our understanding of what fuzzers do, how we test things, so on and so forth, and that limits us in both research and practice. So, let's begin. Part 1, what even is testing? So, many of you came to this talk probably because you have this question. But actually, this is the wrong question. This is the right question, right? How do I test a program? Actually, this still isn't even the right question. This is the real question. What does it even mean to test something, right? So, many people might start by thinking about testing of a program as literally just directly inspecting it, right? But that doesn't really tell us much. Right? We can only really know if a program behaves in a certain way if we actually try it, right? If we actually do something with it and see if it behaves in the way that we expect. And this is typically known as empirical testing, right? And it's kind of like the scientific method, the fuck around and find out method, right? Basically, you start off by proposing a falsifiable hypothesis about your program. That means something that you can actually show to be false, not something that you can just generally claim to be true. Then you run an experiment and you collect some results, and then you check if those results falsify your hypothesis, right? Because if they falsify your hypothesis, you know that your program has a bug, right? Okay, so let's do a test. I have a function called doThing, and it accepts a string, and it returns a Boolean. It returns a Boolean if the string contains only ASCII characters. So I might run one test with hello world. Okay, yep, that returns true. I run another test. This is a test. Great. I run a third test with some emojis. Doesn't pass. Those aren't ASCII. And you can see this here. I have a test specification which explains what the program should do. I have a test result telling me whether or not, well, in this case, I assert that the emojis are ASCII. That isn't true, so the test fails. Right? And then I have some input. And now you might ask yourself, how do we know that this is a good set of tests? Well, you can't in the general case, right? Because you don't actually know what's happening in that program, and you don't necessarily show that every possible case has been considered, right? That's kind of the point of empirical testing. You're trying to disprove something, not prove something. So we can't show that it is complete, but we can measure how completely we've tested it according to certain criteria. So let's look at our function again. It's to accept a string, right? Now, a string represents some input space, basically the space of all strings that you could possibly imagine firing into this program, right? And that might be hello world, that might be this is a test, that might be emojis that I forgot to remove the link from. But fundamentally, you're working with some set of inputs that represents all possible inputs you could submit to a program. We're testing a finite subset of them. Okay, now imagine that my program looks something like this. It's basically just a for loop, and I check, is this character an ASCII one? No, return false. Otherwise, keep going, right? And we can think about this, we can think about the tests that we applied earlier in terms of the flow through the program that they took, right? So for example, the emojis took this path where they actually entered that condition of not ASCII. We have this other one which actually goes through the loop and explores this path but never takes it. And then finally, there's a secret third option, which is not entering the loop at all, which represents all three real cases, right? And this is 100% code coverage, right? What we call this is a subdivision of the input space. Some of you who are old school might represent this as partition testing, but technically speaking, we're not partitioning the space, we're subdividing it into technically not mutually exclusive subsets. Anyway, it doesn't matter. It's not to scale because there are a lot more things that contain emojis than not, in fact, infinitely more, but whatever, this doesn't matter. As long as these two functions are correct, the cars and is ASCII, right? This is probably a pretty good test, right? We've tested all the paths. Okay, ship it. The problem is, there are actually other ways to partition, right? Coverage is just easy and common, and so as a result, it's the one we use the most. But it's still pretty good. And the intuition behind this is simple. If we have a partitioning or a subdivision of the input space that's aligned with the program implementation, it's typically a pretty good indicator of how well a program is tested when we cover those partitions, right? Because, well, the bugs are aligned with how we implement it, not what our inputs look like, right? That's the intuition, at least. And this is where we get into what fuzzing actually is, right? So I have two ways of looking at the same input space, right? I can either sample from this input space directly by just randomly picking strings out of it, right? Which is called generative fuzzing, basically just slurping out information from the input space. And then I have an alternative way, which is to take existing inputs and change them every once in a while and make new inputs, right? And this allows us to traverse the input space, and it's called mutational fuzzing, right? Basically just iteratively transforming the input. And these have different features, right? With generative fuzzing, we typically are going to be using a grammar, and this, it's nice and it's not nice, right? Not nice first. You have typically a limited radius. I'll get back to that. You require an input specification, what the inputs are actually allowed to be. Typically, you're not going to have a whole lot of luck if you just pipe dev random into your program. And we don't really use feedback from our program, which kind of sucks. But also the nice thing is we don't need to take program feedback at all. So that means that these are very flexible, right? We can use them basically anywhere without having any information from the program. But as I said, you have a limited radius. I can only really generate in a very small subset of the possible inputs, right? If I have a grammar generator, which is going to be picking, maybe I make a bigger string, maybe I make a smaller string, right? If you make that decision over and over again, you are going to tend to make smaller strings, right? And as I said earlier, it's not aligned to the program-based partitions, and because it's not aligned to the program-based partitions, we may not expect it to perform as well. Okay, so what about mutational testing? Well, you start off with an input, and then you have some probability distribution that describes the set of inputs that you could mutate into, right? And so if we, in that space, cross a partition, right, then we take that new input and we add it to our list of inputs from which to mutate from. Then, from that input, we have a new probability distribution function which describes where our next input will appear, right? And so we apply another mutation and we get some input that crosses that boundary again, and we go on and go on. And basically what we're doing is we're progressively searching the program by traversing the partitions of the input space that we can monitor based off of the features of the program, right? And this is known as guided mutational fuzzing, right? We're traversing the input space based off of the guidance of these partitions. Okay, and this is pretty cool, right? So using program feedback, we're able to explore the program according to its structure, according to its implementation, right? Which, based on our intuition earlier, should allow us to test the program better, right? It ensures local generation, right? So instead of just generating random inputs which are going to be uniformly distributed across the space that I can sample from, it's going to be sampled relative to inputs that are already in certain partitions. So we're going to be testing those partitions more specifically, right? Theoretically. And yeah, I already said that. I'm going to skip that. So surely, because we have this awesome system that allows us to explore the input space, we are going to find all of the bugs. Well, there are probably other partitions that you couldn't reach from your mutations because you just happen to have a bad draw, and maybe the bug's over there, or maybe it's in a space that you already reached, but now you're not actually traversing that way anymore because you already found something in that partition. Are there other things that we're missing? Okay, for this next segment, I'm going to need 15 volunteers. Don't worry, you don't need to get up. Just real quick, if you want to join in, feel free to scan this. At 15, it will self-close. Sorry, I literally can't see if it's more than 15, but let's go. So, go ahead and join. All right, we got 15 volunteers, right? Who's familiar with the video game Sokoban? Any hands? Awesome. Okay, this is the warehouse keeper game. Basically, as you can see, our contestants are moving around. They're pushing boxes into places, and their goal is to try to move all of the crates into the target positions, right? The game is pretty simple. Your inputs are move left, move up, move right, move down, and undo. And that's all I give you. Fun fact about this. Incredibly hard problem to solve, these puzzles. For those of you who are time complexity and coding complexity enjoyers, this is a NP hard problem, and it's p-space complete to solve this. And oh, by the way, if you want to prove that something is unsolvable, you have to do it in exponential time. Lower bound. So while these guys are cooking away trying to solve this, I'm going to cheat. I'm going to join myself with a fuzzer. Go ahead. Look at me go. Oh, I've solved it. And we can see just how complex this is, right? I'm currently going through, me specifically, not the game, not the fuzzer. I'm currently solving this by walking around, and you can see the solution. It requires a little bit more finesse than simply pushing the crate to the nearest box, right? As you can see, this game is complicated, right? And there's a reason why people have been trying to figure out better ways to solve this. I'm going to give people a couple of more seconds to maybe try to figure it out, but don't be alarmed if you don't. It took me like 15 minutes to actually solve this. I'm kind of bad at this game. Okay. Anyway, does everybody have a good handle on what Sokoban is at this point? You can see what's happening on the screen. You can see how it can be a rather complex game. Great. So this is going to be the springboard for the rest of this talk. Right? Because Sokoban is, in a lot of ways, a very nice representation of everything that can go wrong in fuzzing. And even though I showed a fuzzer winning that game, I actually cheated and picked a puzzle for which fuzzers are actually very good at solving these. So, part 2, how can we look at puzzles and think about solving fuzzer problems in the space of puzzles? Okay, so what's in a game, right? Basically, we have a user who is inputting moves, keyword input. We have an objective. We have some test goal, if you will. So clearly, because every hammer needs a nail, this is testing, right? So we can fuzz this, right? It's pretty similar in structure to our test with the ASCII characters, yes? Structurally, it looks pretty similar. Oh, but there's a couple of pesky mutations happening. It looks like we're not just checking each character anymore. Now we're actually doing something with those characters, right? So how bad could it possibly be? I mean, surely this kind of state accumulation couldn't be too much of a problem. Well, here's a comparable problem that I ran with libafl for a bit. Any takes on how long it takes the fuzzer to figure out how to get v equal to 4? Yeah, it takes about 250,000 to 34 million executions of libafl with havoc to actually find v equals 4, right? This is not a hard program, right? State is actually, surprisingly, really hard to solve. So the thing is, right, think about it in terms of the Sokoban puzzles again, right? We have one function which describes all Sokoban puzzles, right? This one function describes all Sokoban puzzles. And what that means for us, right, is that if we use a fuzzer, which is code coverage guided, right, every single puzzle has the same guidance, which is insane. That does not work. So most software is actually highly stateful. You might be familiar with typical uses of this. We have client servers. We have interactive programs like GUIs and stuff. But like, that may be what most user-facing software is, but this also applies to other kinds of software. I mean, think about a CPU, right? A CPU really is just a Sokoban puzzle with more steps, right? You know, like, think about compilers, right? The inherent complexity and the enormous amount of state that we build when we're actually building programs, right? Think about databases, right? Interactions in databases that have to be sequential in order to actually find different behavior in these programs. And, you know, I really think this is important to stress, right? Because we talked about how partitioning earlier really should be giving us a better indicator of how well we've tested something. But partitioning in the ways that we do classically really just does not model state very well at all. And we just don't have a general way to do it. So, yeah, that's just an unfortunate reality of what we're doing. So let's think about another problem, right? What happens when we actually mutate an input, right? I might say that a mutation here is to apply a move, right? I moved left. Oh. Instant replay. Okay, great. Now we can move up. Now we can move right. And okay, great, I have the sequence of inputs. But now what happens if I mutate something near the beginning of that sequence? Right? Well, I move right, and then I move up, and then I die, right? So the problem here is that because I mutated a beginning part of the input, it changed how the later part of the input was interpreted. And this is actually a known effect. This is something called the havoc effect, which comes from this actually surprisingly recent paper on mutation in the context of parametric input generator. We'll get to that in a second. But basically, their claim is that the havoc effect is where small mutations cause these destructive changes to later parts of the input or other parts of the input. And in that context, what they're doing is they basically have some structure that they want to generate with fuzzing. But making mutators for arbitrary structures is kind of hard. So what they do is they take some bytes and then they derive some transformation where they take random bits and they turn it into structured data, right? Then the idea is if I mutate that random bit sequence, well, I get a mutated input in the structured domain. The only problem is that what they found is, and a conclusion that many of you I'm sure have seen in the practice, is that small changes to the byte sequence early can cause large changes to the derived input because we're changing how that later part is interpreted. And in Sokoban, we can see this directly, right? This is the exact input that I gave earlier, right? When we mutated that left into a right, it completely broke our input. It was totally invalid. What this means is that the havoc effect. Yeah, I'm going to wait for a sec. Ah, there we go. Sweet. Okay. What that means for us is that the results of that study don't just affect parametric input generators. It also affects random programs, like all programs really that use any form of reinterpretation of one part of the input to affect another. Think about networking, right? If I change the type of the network packet, it's going to change how the packet is interpreted, right? So what this tells us is that the mutations are just not that local, right? So one of our base assumptions about how good mutational fuzzing is just broke, right? That's kind of a big problem, right? Because similar to the issues that are caused by statefulness, these mutations can actually cause the other parts of the input to be reinterpreted. So without even running the program, we're still having this reinterpretation problem where we're limiting our exploration. And also it means that our local search isn't guaranteed, right? If we're in a partition and we mutate, that does not mean we'll end up in the same partition, right? In fact, it much more likely means that we'll end up very far away, testing something else entirely. That means that our inputs are not as well distributed as we thought. Okay, let's do another one. All right, I'm exploring with mutational fuzzer and I find this path. Great, not the solution. What about this one? Still not the solution. Another one? No. Still no. Finally, I found it. What just happened? Right. Well, the fuzzer is going to explore different paths in the program, right? But ultimately, it's going to get into different places every time that it runs, right? If I were to run my fuzzer again, right, it would take a completely different amount of time, or it may not solve the puzzle at all, because it would get stuck in a local optimum. Because I don't have very good guidance for Sokoban puzzles, actually. And this is also a known conclusion. There's a paper by some people in my group, actually, where basically what they formalized, I guess, is that novelty search is not particularly good at rediscovering different ways of going down the same path. Once you've seen something once, you never want to see it again, right? And what this means is that you may have other inputs which would be more valuable for getting to the next point in your program, the next point in your exploration of the program, but you'll never actually take them because you already have discovered something that makes that not novel. That might be a little bit unclear. Basically, there are two decisions, right? We can either make better guidance, in which case we'll actually explore the program better, but this is maybe impossible, or we can restart intermittently and just hope that we're able to explore the program a little better, right? And this kind of comes to problem 3, which is that this guidance is really limited. We constantly get stuck in fuzzing, where we get into these local optima that don't allow us to test the program thoroughly. So, another assumption, gone. We can't get everywhere. Yeah, so whether it's by state or it's a limitation of the mutation or something else, the novelty search that fuzzing uses in guided mutational fuzzing will often get stuck. It will not explore the program thoroughly, and in some cases, it may not ever be able to reach certain parts of the program. Okay, last one, I promise. So I move left. Are these two states really that different? Nothing's really changed, has it? Yeah. So the thing is, right, we can think about input in different ways, right? We might think of Sokoban as a program where we're submitting a sequence of moves, right? But that's not the only way we can think about it, right? In fact, if we look at different ways to represent testing the same program, right? What happens, for example, if we're looking at XML documents, right? Libraries which handle XML documents, right? You can either send them an XML document, tell them to parse it, and then quit, or you can use the library to make XML documents programmatically, right? This allows us to basically project a different version of the input into our program. So we might have some original input space and we map it into a new input space. And what that means is that not only do our bugs realign, but so do our partitions. So we're actually able to explore the program differently. In other words, by providing the input differently, we explore and we test the program differently, right? And that's actually kind of insane when you think about it. If I apply this to Sokoban, right, instead of saying, oh, just move left, if I look at all the boxes that I can move at any given position, I can reduce a mutation to move the box, right? So instead of just saying left, I can say move the box with the label 7 left 4 times, right? That might not seem like a lot, but that's the only reason that my fuzzer was able to beat anyone there, right? Testing programs with just one type of input is just not going to work, right? And this kind of comes back to our original intuition, right? If we align our inputs that we test to the partitions of the program, we test the program well. That was our intuition. But in reality, this only applies as long as the objective, so the bugs that we're looking for, the mutations, and the guidance that we apply in order to explore that program are all aligned with the program. Otherwise, we're just getting lucky when we find bugs. Right? And reformatting inputs like this is really meaningful. I mean, if we look back at this libxml2 fuzzer, right? libxml2 is one of the most aggressively tested programs on the planet. When they submitted this patch, the other 75 commits fix issues discovered by this. This is one of the most widely tested programs in the world. And just changing the way that we think about the input to this program found a ton of new issues. Okay, so what's next? First of all, sorry, there just really isn't enough time to truly demystify fuzzers, right? Mostly because I don't actually know. In fact, nobody really knows. And the thing is that there are so many papers that we could cover and go over that have really started to explore this, but not thoroughly yet. We have stuff from the 70s and 80s and 90s that already figured out a lot of this stuff about partition testing that we aren't using because in the security domain, we're more about demos and bugs and findings, right? And there are other things in the security and the software testing community that are beginning to address this, but we're just not there yet. We're not there yet with our understanding of how to generally talk about how inputs and mutations relate to program guidance, right? And like, I had whole other sections of this talk that I wanted to do. I wanted to talk about this little game from my childhood, or the entirety of the evolutionary algorithms and genetic programming field. But there just isn't enough time. So I just want to conclude by saying we actually understand very little about how fuzzing works. Nobody really knows what's going on, right? We don't really understand the distribution of bugs with regards to the program structure, right? We don't understand where they are, how to trigger them, so on and so forth. We don't really understand the relationship of the input, the mutations, and the guidance that we take from the program, and we have no idea what the limitations of our fuzzers are, whether it comes to the specific programs that we're testing or in general, trying to make general claims about the programs that we're testing. And this program input interaction is really critical, but we just don't have the means to describe it yet. So to finish it off and make it a little bit more hopeful, I know this talk is titled Demystifying Fuzzer Behavior, but the truth is that only you, the practitioner, can do this. Right? Per program, you have to do this. So if anything, take away from this talk, as practitioners, you must really think critically with regards to how fuzzers are actually interacting with the programs, right? And researchers in the room, please, we must make it possible for practitioners to understand things better, right? We need to make models for the relationships between input programs and the mutations thereon. We need to make it possible for practitioners to understand things by making our research and fuzzers more accessible. And we need to reject this rat race of incremental work that we're doing right now of trying to find a little bit more coverage. Because otherwise, we're just going to be stuck in the local optima. And really, to hammer this home, we need to go back to empirical testing, right? the fuck around, find out, right? The academic security community really needs to re-engage with this critical approach to science. We're not trying to prove that our tools are good. We're trying to prove that we don't understand something or that our existing understanding is limited, right? We don't show that something is true. We are trying everything in our power to show that it isn't. Right? Okay. Thank you very much for attending my talk. I want to give some thanks first. Hold on. I need to thank Surreal Ember, who made all the pixel art for the Sokoban, and also a completely different program that we didn't even use. I want to thank my colleagues, my friends, and my partner for helping me test early iterations of this. Yes, I see you laughing. And also 2Swap, who I was going to put some video segments from. If you haven't seen their stuff, please go watch it. It's so cool. All right, with that, now I'm actually done. Thank you.
Thank you so much for this really cool talk. Not only have you built awareness for this, but you have managed to completely fill Hall G on day 1 of Congress, so congratulations.
Let's go!
If you are leaving the room, please be quiet. And if you have questions, we have 4 mics lined up here. Please stand next to them and we will call you out. As you're leaving, be quiet to let everybody else enjoy the rest of the talk. On the side of the Signal Angel, do we have a question already?
Yes, question from the internet. What do you think about formal testing methods? Proofs beat tests, they say.
That would be great if it actually worked at scale. The thing is that for most applications, you simply cannot formally prove things. And also, it requires the human in the loop to actually be able to encode the formal properties correctly, which is significantly less typical than I would hope. That's not to say it doesn't have its place. I mean, there are plenty of formal methods, applications for like CPU verification, and yet we still find things like Spectre and Meltdown, right? So at the end of the day, I really think that there's just too much software to really test, and empirical methods allow us to bridge that gap at least a little bit, right?
Let's head on to the room. Mic number 3.
About the havoc effect, I have a question related to how we express the problem as related to state. Mm-hmm. To my understanding, things we can express using mutable state, we can also express using combinators like iter and fold and map in like functional programming languages where we prefer immutability, right? So is there a way to express this problem agnostic to the divide from mutable state to like a recursive functional immutable programming?
It's actually funny you mentioned that, because my implementation of Sokoban state is actually a functional applicator. So I basically iterate over the moves and then I fold over the state, right? So state application, right? So it doesn't really matter whether or not you are using a mutable state representation or not. The problem is whether or not you are using different parts of the input with respect to each other that can either be in terms of state, like the current value and the application, or it can be something else entirely. I mean, it really just matters more on how we're interpreting the input and whether or not certain segments of the input can cause other segments to be reinterpreted in other ways, right? And in this case, state is the cause for this, but it can be a whole lot of other things.
Mic 4.
Thank you for the talk. If the inputs, in this case the level and the crates, were randomized, would the fuzzer fail? And if so, would neural networks be a better solution?
It's funny you mentioned that. The current best Sokoban solver that we know of was recently written by Meta, and it's actually very good, and it does use some amount of reinforcement learning and machine learning in order to accomplish that. The thing is that we don't actually know how good it is because we're using human-derived puzzles to test it, right? How to actually generate hard Sokoban puzzles is unsolved. Nobody's really done this in practice. And also, any generator that we would produce would necessarily be some subset with common features that we could learn from, right? So the question, are neural models necessarily better? Maybe. I mean, at the end of the day, we can probably bully these down into random search again, if we really wanted to. Does that make sense?
Yeah, perfectly. Thanks.
Mic number 2.
Yeah, thank you. I just wanted to quickly ask you about your opinion regarding Google's open source fuzzing projects. And to my understanding, this is a lot of effort going into trying to find optimal fuzzing configuration and how to fuzz things. Do you think this is almost wasted compute?
I don't think it wastes compute, right? Even though my talk today was a little bit on the dismal side, at the end of the day, right, we're working with what we got, right? So empirical testing, we're basically doing a random search. We're applying some either local search with mutational or totally random with generative. When it boils down to it, right, we still have a better chance of finding bugs if we're doing this search than if we're not doing this search, right? And I think Google's done a lot of good in making things like cluster fuzz widely available, OSS fuzz, these things. And I think they're doing interesting things with like these fuzz harness generators as well. But I think those fuzz harness generators are limited because they don't understand input projection. That's a relatively new concept that we're not really looking into yet. There are things like Hopper, this paper Hopper, that are doing these input generation, or this input transformation as harness generation. Even that's still limited. Any effort expended is good, is my general take. I don't think we're wasting compute.
Thank you.
Mic number 3.
Yes, great talk. Thank you. So for the Sokoban example, there was a very clear delineation of when the puzzle is solved. You have a target to reach, but in many other fuzzing applications, you don't have necessarily such a clear idea of when the problem is solved or not.
Right.
So how do you determine what, like, if you have found an interesting state as opposed to just some new state that might not be relevant?
That is the question. So there are kind of two questions encoded there. One is the, how do we know if something is new? How do we know if it's novel? Which we don't. The other question is the test oracle problem, which is how do we know if something is in an objective state or in a search state, right? And that's been around since the 1950s. I mean, we're no closer to solving the test oracle problem than we were. These are going to be things that need to be resolved per program with program level specification and, in a lot of cases, human-derived oracles for figuring out whether or not something is a objective or crash or whatever, right? Or whether or not it's just normal behavior.
I guess normally they just do does it segfault or not, but that's not necessarily the best one.
Yeah, I mean, if you want, I love differential oracles, property-based oracles. Like, there are plenty of different ways to do this. Highly recommend. There's a lot of resources out there, and I would honestly love if we made a better book to actually guide people to understand these things and have these resources available, but we don't right now. So I will try to send it, yeah.
And that concludes our Q&A session for this talk. If you do have questions, and I see there's still people at the mics, please grab Addison after the talk or catch them online on whatever website resources are available.
Yeah, just the website that I showed on the screen earlier. You can just go to that. It's fine.
So thank you so much for the wonderful talk, Addison.